Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show thermal analysis using ANSYS mechanical APDL. For modeling, we have considered one hemispherical container with 3 different materials with different thermal conductivities. We have modeled this vessel with SolidWorks and saved that part in IGS format. First of all, we have to import that model from files. Let us import that model. Let us browse it from the desktop where we have saved this model. This was saved in a new folder by the name of assembly IGS. So this is the model. We have taken a hemispherical part of a container. Let us select different views of this one. We have considered 3 different materials, right? First one is having thermal conductivity 0.02 per meter degree Kelvin. Second one is 0.06 and the third one is 0.16 watt per meter degree Kelvin. These are the thermal conductivities of the 3 different materials. Okay, and actually we have assembled all these 3 different parts. Let us provide title of this one as thermal analysis. Okay, then plot replot, it will show the content thermal analysis at the lower left corner. We can create a directory and that what can be saved in the directory. We have already created a directory in the desktop by the name of new folder. Okay, starting our analysis from preferences, we want a thermal analysis. So thermal analysis checked in. Next one, preprocessor, element type to be added as nothing is there, so we have to add the element. We are taking solid element and node we are selecting as 20 node 279. More the node meta is a solution, so we are taking 20 node 279. Okay, close it. Next one, material properties should be specified. Material models, thermal conductivity. It is isotropic, that means throughout the material properties will be same. Initial thermal conductivity we are providing 0.02 watt per meter degree Kelvin. Let us provide second material, new model, material ID 2. Let us provide thermal conductivity to this one as 0.06. okay, and the third one, material, new model, and material ID is 3. Let us provide thermal conductivity to this one as 0.16 watt per meter degree Kelvin. So we have provided 3 different materials of thermal conductivity, 0.02, 0.06 and 0.16 watt per meter degree Kelvin. Now meshing. We have to see the mesh attributes. That means we have to provide those materials with thermal conductivities. Mesh attributes, we can select peaked volumes. That means as per specific volume we have to provide the material and accordingly it will be meshed. Okay, so let us select any one. This is the first shell having inner diameter as 400 millimeter. Let us select that one and we have to provide material number 1 for this inner shell. So material number is 1, applied. Now the second one to be selected. This is the second material. Okay, so we have to apply material for that one. We have to apply second material number 2 for the second hemispherical part. Apply. Now the third one, let us select the third one. This is the third container. Okay, and we have to provide a specific material for this one as material number 3. Okay, so we have defined 3 different materials. Inner one as material number 1 with thermal conductivity 0.02 watt per meter degree Kelvin. The second shell having material ID number 2 and with thermal conductivity 0.06 watt per meter degree Kelvin. And the third one with material ID 3 with a specific thermal conductivity of 0.16 watt per meter degree Kelvin. So material has been defined. Next one, to go for meshing. For meshing, we are having different options. Let us select size controls, smart size, and we are selecting basic. Size level is off. We can go for finite mesh, select 1. Okay, then let us go for mesh, volume, free. Let us select all the volumes, so pick all. Meshing has already been started. It is violating some constraints, okay, but meshing is done. If you want to go for further meshing, it can be done. Modified mesh can be done. Let us go for further meshing. Modify mesh, refine at all. Okay, so mesh refinement is going on. It is fine. I think it is okay. Next one, you have to apply boundary conditions. That means inside you have to provide a temperature of 140 degrees centigrade, and atmospheric temperature outside it will be 30 degrees centigrade. Our task will be to find out the interface temperatures. Okay, so we have to apply boundary conditions from. Still pre-processing is going on. Meshing is complete. We have to go for applying boundary conditions. So solution, define load, apply thermal temperature to be applied on specific areas, but before that you have to identify the areas, because selection of areas in ANSYS is a little bit difficult one, so better to identify those areas in terms of numbers, then you can provide area numbers easily. So what we'll do is, let us plot areas. These are the different areas, and we have to provide name for these different plotting areas, plot controls, numbering, and we want to make the numbering of areas to be on. Okay, now you can see different colors with different numbers, right? When you see the numbers inside, this inside surface area is 10, and if you want to see the outside one, outside area is 17. So we got two different specific locations for applying boundary conditions. We have to provide outside area to be 30 degrees centigrade at surface area number 17, and inside you have to provide at area number 10, we have to provide a temperature of 140 degrees centigrade. Okay, so let us rotate this one a little bit. Okay, so inside area is 10. Next one, we can go for these actual elements, plot elements. This is the original model. What we want to do, we have to apply boundary conditions inside surface, inside curved surface. We want to provide a temperature of 140 degrees centigrade and outside to be 30 degrees centigrade. Okay, so apply temperature on areas. Inside surface is area 10, so we can select 10 and apply, and we want to provide a temperature of 140 degrees centigrade at inside curved surface. 140 degrees centigrade applied. Next one, we have to apply temperature at the outer surface to be 30 degrees centigrade. So we have to select the area number as 17. Okay, and temperature to be 30 degrees centigrade. Okay, so boundary conditions have been applied. We don't want to apply other conditions like convection from outer surface, so we are not bothered about convection. We are considering only conduction through different composite surfaces, right? Pre-processing is complete. We have to go for processing. That means we have to run it. Solve current ls. If everything is right, it will show solution is done. Otherwise, it will show some error message will be there. So it is calculating and it is showing the solution is done. Everything is perfect. Your processing is complete. We can go for post-processing. That means we want to have the results. And post-processing can be obtained from general post-processing. You want to see results in the form of plot results. Plotting and listing to be checked. plot results, contour plot, nodal solution, and we want to have temperature, nodal solution, degrees of freedom solution, nodal temperature. Okay, so you can see these things, temperature at different interfaces, at different surface. We can see better to see these things from some specific plane. Let us see these things from backside. So we can see here clearly maximum temperature at the inner surface is 140 degrees centigrade, and as it is approaching outside, its temperature is reducing at different levels. That means its temperature is ranging from 140 to 54 degrees centigrade in the first hemispherical shell. In the second one, we can see the ranges from 54 to 42 degrees centigrade, and in the third shell the temperature ranges 42 to 30 degrees centigrade. These are the temperature ranges. We can have the specific temperature at different interfaces also. That one will show through these listing results. Okay, and excluding that one, we can see some other thing like nodal solution, and thermal gradient also can be checked. Thermal gradient for vector sum thermal gradient we can see. So maximum is 2.16 and the minimum is 0.08. This is thermal gradient. Next one we want to see the thermal flux for vector sum. Maximum thermal flux is 0.04 and minimum one is 0.01. Okay, now all these things you can see in the form of listing results also. Let us see list results and nodal solution, DOF solution, nodal temperature. Okay, like the previous case, you can see here the data in the form of all these temperature at different nodes, and you can see here maximum temperature is 140 degrees centigrade, that is inside surface, and that is at node number 1. At different nodes we are having different temperatures, right? At, you can see at 60244 node number, temperature is 90.549 degrees centigrade. Our task is to have the temperature at different interfaces of the different materials, right? We can have this specific temperature at different locations. For that one, what we have to do is we have to see the numbers of nodes at the different locations, and then actually across this periphery temperature distribution will be equal. So what we'll do is plot controls, numbering. You want to see the node numbers to be on. Okay, these are the different nodes available at different interfaces, right? So we can see that at any specific location across the periphery, the temperature distribution is symmetric. Let us see any specific location from plot controls, pan, zoom, rotate, and you want to have a box zoom for any specific location. Let us see these things, the temperatures. Let us see the temperature at node 135 and 223 and 315. These are the different nodes at different interfaces. First node you can see at 590, this one at this location. At this location temperature is actually 140 degrees centigrade, and we have to find the temperature as different locations at here and here, right? First interface is this one, and this is second, and this is the third one. Third one is already known, that is temperature 30 degrees centigrade. Our task is to have the temperature at this location and this location, right? So we can find out the temperature at node number 135 and 223. Okay, you can remember this 135 and 223. So we have to go for list results, nodal solution, temperature. Okay, listing results are required. That means we want to see the temperature at node number 223 and 315. You can see it, 223 and 315. These are the node numbers. First one is node number, second one is the temperature. We can vary this one, 223 and 135. First one will check the temperature at node number 135. You can see at node number 135 temperature is 54 degrees centigrade. That means you can say that first interface temperature is 54 degrees centigrade, right? And the second one that is at node number 223. temperature is 35.1 degrees centigrade. Okay, so we got the interface temperatures as 54 and 35 degrees centigrade. First temperature T1 at the inside surface of this hemispherical shell is 140 degrees centigrade. Second one 54 degrees centigrade. Third one is 35, and the final one, that is at the outside surface, it is 30 degrees centigrade. These are the temperatures available from this thermal analysis using ANSYS. Next one, we will validate these results with respect to manual calculations. Let us see these manual results. We have considered three different shells of different radius. You can see the thermal circuit diagram. We can see the temperature at different interfaces. T1 is the temperature at the inside surface, T2 the second interface, T3 is the third one, and T4 is the last one. Within these temperatures, T1 is 140 degrees centigrade, which is known, and T4 is also 30 degrees centigrade, which is known. We have to find out temperature T2 and T3. From the thermal circuit diagram, you can see that in between T1 to T2 we are having thermal resistance RTH1, and between T2 to T3 thermal resistance RTH2, and in between T3 and T4 we are having RTH3. Let us drag this one, where you can see the heat transfer rate equal to del T by R theoretical. R theoretical is the total resistance. Now in this case we know that heat transfer rate to all the surfaces are equal. Total heat transfer rate equal to del T by R theoretical 1. Here R theoretical 1 is equal to R2 minus R1 by 4 pi K 1 R1 R2. So all this data is available here. So we can from this data we can find out R theoretical 1, that is thermal resistance for the first circuit. Similarly, thermal resistance for the second circuit is 0.88, and for the third circuit it is 0.23. Applying all this data, we can find the heat transfer rate equal to 21.57 joules per second, that is 21.57 watt. And as we know that heat transfer rate for all the surfaces is equal, like if we see that heat transfer rate from T1 to T2 is equal to same heat transfer rate from T2 to T3. So applying this one, you can find out Q dot heat transfer rate equal to T1 minus T2 divided by R theoretical 1. In this case, we know T1 and R theoretical 1 and Q dot is known. So we can have the value of T2, that is first interface temperature. It is 54.17 degrees centigrade, which is exactly validated with our analysis using ANSYS mechanical APDL. Similarly, for the second interface temperature, we know that Q dot equal to T2 minus T3 divided by R theoretical 2. Here in this case Q dot is known, that is heat transfer rate. T2 is also known, that is we obtained right now, and T3 is unknown. So applying all this data, we can have T3 equal to 35.09 degrees centigrade, which is exactly same what we got from our ANSYS thermal analysis. Okay, so this is all about today's thermal analysis using ANSYS mechanical APDL. In this case, we have taken three different hemispherical vessels with different diameters. And inside you have provided a constant temperature of 140 degrees centigrade, and outside it was 30 degrees centigrade. And through this analysis we got the interface temperatures. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.